Alright, so today we're diving into the Nernst equation and how it explains the workings of a galvanic cell. Picture a galvanic cell with two electrodes. Let's start with one side having a solid zinc electrode in a 1 molar solution of zinc ions, and on the other side, a solid copper electrode in a 1 molar solution of copper ions. Copper ions make the solution appear blue, while zinc ions don't give any color, so that side stays colorless. In a galvanic cell, these two electrodes are connected by a wire with a switch, and there's a salt bridge linking the compartments. The salt bridge allows electrical charge to travel between the two solutions, completing the circuit. Now, to kick things off, we'll close the switch, allowing electrons to start flowing through the wire. To understand the cell potential or voltage of this galvanic cell, we use the Nernst equation. Here's how it looks. The E represents the instantaneous voltage, which is the voltage at a specific moment in time. The E naught is the standard voltage of the galvanic cell. Next, N stands for the number of moles of electrons transferred in the redox reaction, while Q is the reaction quotient. The reaction quotient is essentially the ratio of the concentration of products to reactants. But here's the key point. When calculating reaction quotient, we only include the concentrations of the ions in the solution, not the pure solids like the zinc and copper electrodes. Let's break this down into two half reactions. In the first half reaction, solid zinc loses 2 electrons, and in the second, copper ions in the solution gain 2 electrons. Remember the mnemonic LEO, the lion goes GER, loss of electrons is oxidation, and gain of electrons is reduction. That means the zinc electrode is oxidized, and the copper ions are reduced. To get our overall equation, we simply add these two half reactions together. Both ion concentrations are 1.0 molar under standard conditions, so when we plug this into our Q value, we get 1. Since we're under standard conditions, our Nernst equation simplifies, and we find that the instantaneous voltage E is equal to our standard voltage, which is plus 1.10 volts. Now, what happens if we change things up? Let's increase the copper ion concentration to 10.0 molar while keeping zinc ions at 1.0 molar. With this change, Q becomes 0.10. Plugging this into the Nernst equation, we find our new instantaneous voltage has increased to plus 1.13 volts. Now, let's flip things. We keep copper ions at 1.0 molar, but increase zinc ions to 10.0 molar. This time, Q equals 10.0. Substituting this into the Nernst equation, our voltage drops to plus 1.07 volts. As you can see, increasing Q decreases the cell voltage. Now let's compare Q to the equilibrium constant K. For this reaction, K is an enormous value, 1.54 times 10 to the 37th power. If Q is less than K, the reaction moves forward, converting reactants to products, and the voltage remains positive. But what happens when Q finally equals K? At that point, the second term in the Nernst equation equals the first term, resulting in an overall voltage of 0. The reaction stops, and the galvanic cell has reached equilibrium. The zinc electrode would be used up, and the copper electrode would have grown in size. Now, let's take it a step further. What if we have a concentration cell, where both electrodes are made of the same metal, say nickel, but the ion concentrations are different? Imagine one side with 1.0 molar nickel ions, and the other side with a dilute 1.00 times 10 to the negative third molar solution. In this concentration cell, Q equals 1.00 times 10 to the negative third. Substituting this into the Nernst equation, and knowing N is 2 and E is 0 because it's the same metal, we find that the instantaneous voltage is plus 0.0888 volts. This positive voltage tells us the reaction is spontaneous. Equilibrium is reached when both compartments have equal concentrations of nickel ions. At this point, Q equals 1, the logarithm of Q becomes 0, and the voltage drops to 0. Alright, quick recap. The Nernst equation is a powerful tool that lets us calculate the instantaneous voltage of a galvanic or concentration cell at any given moment. As long as Q is less than K, the reaction is spontaneous, and there's a voltage, but when Q equals K, the cell reaches equilibrium and the voltage drops to 0. Remember, adjusting ion concentrations directly affects the voltage, giving us insight into the reaction's direction. And that's how the Nernst equation reveals the secrets of galvanic and concentration cells. If you found this breakdown helpful and want to master more topics like this, be sure to check out King of the Curve, our platform offers in-depth resources helping you stay ahead in your studies. Don't forget to like this video, subscribe to our channel, and hit that notification bell to stay updated with our latest content. Thanks for tuning in, and see you next time.